In this video, we're going to take a look at the NTP leap indicator field and how it's used to warn NTP clients about timing issues. First, we'll take a look at what the leap indicator tells us. Then we'll have a look at the different warning states, and finally we'll demonstrate each state using our test network. Before we start, I'll just give you a quick overview of our hardware setup today. We're using this mini PC as the NTP client. This is running Windows 11 and we're just using the standard Windows time service to trigger our NTP requests. We're using a Sync Defender network time server as our NTP server, and this is locked to GPS. And the mini PC and the NTP server are connected together via this Ethernet switch that I have here. We've put links to everything that we're using in this video in the description box below. Okay, so that's the setup covered. Now let's take a look at what the leap indicator field tells us. So, the leap indicator is a 2-bit field located at the very start of every NTP packet. It's one of the most important fields that an NTP client uses to decide whether to trust the time from a server. The leap indicator serves two main purposes. It tells the client whether the server's time has ever been properly set, and it warns of an impending leap second. As a side note here, leap seconds are a fascinating subject and have been the cause of some well-documented IT failures over the years. This might all be a thing of the past soon though, as they are planned to be phased out. Let me know in the comments below if you'd like us to cover this in a future video. So that's the basics of what the leap indicator tells us. Now let's have a look at the different warning states. There are 4 possible values for the leap indicator field. A value of 0 means no warning. This indicates that the server's time has been set and there is no leap second warning. This is what you would expect to see during normal operation when everything is working correctly. A value of 1 means last minute of the day has 61 seconds. This warns that a positive leap second will be added at the end of the current day. A value of 2 means last minute of the day has 59 seconds. This warns that a negative leap second will be removed at the end of the current day. Both of these are advanced warnings that allow NTP clients to prepare for the leap second adjustment. A value of 3 means alarm condition or time not set. This is a critical warning that tells the client not to trust the time from this server. This normally indicates that the server has been rebooted and has not yet resynchronized to its time reference. Alternatively, it could indicate some other critical timing issue. So that's the different warning states. Now let's demonstrate each of these states using our test setup. First, let's look at the normal no warning state. If I force the Windows time service to resync, this will send an NTP request to our server. Let's have a look at this in Wireshark. Looking at the NTP server reply packet, we can see the leap indicator is set to 0, which means no warning. This tells us the server's time has been properly set and there is no leap second warning. As an aside here, we can also see the STRATUM is set to 1, as our server is a primary GPS locked server and the reference ID shows GPS as the reference source. If you want to understand more about these other fields, we've done a video on the full NTP packet format. We've also done a video on NTP STRATUM values, and links to both of these videos are in the description below. Now let's demonstrate the time not set alarm condition. I'm going to disconnect the GPS antenna and cycle the mains power on our NTP server to simulate a reboot condition. When an NTP server first starts up, it hasn't yet locked to its reference source, so we'll set the leap indicator to 3 to warn clients not to trust its time. Let me power cycle the server now, and we'll wait a moment for it to come back online. Now let's force another time sync from our Windows client and capture the packets. Looking at the server reply, we can see the leap indicator is now set to 3, which means alarm condition or time not set. Even though the server is responding to requests, it's warning clients that its time cannot be trusted yet. Now let's reconnect the antenna and wait for the server to lock to GPS. Okay then, so the server is now resynchronized. Let's force the Windows time service to resync yet again. If we go back to Wireshark, now we can see the leap indicator is back to 0, no warning. So the client knows the time has been set. Now let's demonstrate the leap second warning states. For this demonstration, I'm going to disconnect the GPS antenna from our server and manually configure it to show a leap second warning. First, let me disconnect the GPS antenna. Now I'll access the server's configuration interface and manually set a positive leap second warning. This simulates what would happen if the server received a leap second announcement from its reference source. Something to note here is that leap seconds are typically only introduced on the last day of June or December. The warning flag will only be visible on these dates. So for our test to work, I'll need to change the date on the server to be one of the standard leap second dates. Okay, so I've manually set the date to the last day of December and I've manually set a positive leap second warning. Let's force another time sync and capture the packets. Looking at the server reply, we can see the leap indicator is now set to 1, which means last minute of the day has 61 seconds. This warns NTP clients that a positive leap second will be added at the end of the current day. Let me change the configuration to show a negative leap second warning instead. Now let's capture another packet. And we can see the leap indicator is set to 2, which means last minute of the day has 59 seconds. This warns that a negative leap second will be removed. So how should an NTP client respond to these different leap indicator states? A well-configured NTP client will typically ignore any server with the leap indicator set to 3, indicating the alarm condition. This prevents the client from setting its clock to an incorrect time. For leap second warnings, the client should prepare for the time adjustment. This normally means adding or removing the extra second at the end of the day, but not all systems work this way. Some systems gradually smear time over many hours by adjusting the speed of the system clock. This ensures a day where a leap second event occurs still contains the standard number of 86,400 seconds. Although some of these seconds are not the same length as a standard SI second. Whichever method is being used, it's obviously really important that all connected systems are using the same method. I think we can all now start to see why leap seconds have been the cause of so many issues over the years. In this video, we've looked at how the NTP leap indicator allows an NTP client to see whether the time has been set on a server and warns of a leap second. But this is just a small part of the NTP packet data. If you'd like to learn about the full NTP data packet and how this is used to set the time on an NTP client device, you might like to watch our video explaining the NTP packet format. The link is on the screen just here.